Here's something nobody expected to say out loud. Scientists had the trajectory of an interstellar object locked down, peer-reviewed, confirmed, and then a new peer-reviewed paper came along and told them they were wrong. 3I Atlas, a visitor from another star system, is not moving the way it should be. It's drifting sideways. Not away from the sun, sideways. And that sideways drift happens to be pointing it directly toward Jupiter's gravitational boundary, which it will reach in roughly 10 days. Jupiter isn't responsible. The object is still outside its influence. So whatever is steering it is doing so entirely on its own. What we found inside the data is what's keeping researchers up at night. If this has hooked you, subscribe to the Skylab, because 3I Atlas is still moving and we are going to track every development as it happens. Also, drop a comment telling me where you are watching from and whether you think scientists have finally got this trajectory right, or whether this object has one more surprise waiting on the other side of March 16th. Now, let's get into it. Something is wrong with the math. Not a little wrong. Not a rounding error, not a measurement glitch that gets corrected in the next software patch. Wrong in the kind of way that makes orbital mechanics specialists sit back in their chairs and stare at the numbers for a long time before saying anything out loud. 3I Atlas, the third confirmed interstellar object ever detected passing through our solar system, is not going where it's supposed to go. A new peer-reviewed analysis dropped just weeks before this object's closest approach to Jupiter, and it has quietly rewritten the trajectory that scientists thought they had locked down. The object is drifting. And the direction it's drifting toward is exactly the one place in the solar system nobody wanted it to drift toward. But let's back up, because if you haven't been following this story, you need to understand what 3I Atlas actually is before you understand why a trajectory correction is so unnerving. We've only ever confirmed 3 objects that originated outside our solar system. The first was Oumuamua, detected in 2017, a strange, elongated, tumbling thing that refused to behave like anything scientists had seen before, accelerated away from the sun without any detectable outgassing, and then vanished before anyone could study it properly. The second was Comet Borisov, spotted in 2019, far more cooperative, far more comet-like, and a relief to scientists who wanted something they could actually model. The third is 3I Atlas, discovered on July 1st, 2025 by the Atlas Survey Telescope in Chile. Another visitor. Another object from another star system, crossing hundreds of trillions of kilometers of interstellar space and arriving in our cosmic neighborhood. These objects are extraordinarily rare to detect. Each one is a scientific event on its own. Each one forces astronomers to update what they think they understand about the objects traveling between stars. And 3I Atlas has been doing something interesting since the moment it arrived. It's been showing behavior that sits just slightly outside what the standard models predict. Not dramatically, not obviously, just slightly. The kind of slightly that accumulates over time and becomes a problem you can no longer ignore. The problem scientists can no longer ignore is this. A new analysis of positional observations, meaning the precise, carefully measured locations of the object tracked over weeks, has revealed that NASA's original trajectory model got something wrong. Specifically, it underestimated the sideways acceleration acting on the object. When scientists first started modeling 3I Atlas, they treated it roughly the way you'd treat any comet approaching the inner solar system. You account for the sun's gravity. You account for outgassing, the jets of gas and vapor that sublimate off a comet's surface when it heats up. You build those forces into your model, and you get a trajectory. That's standard procedure. It works. It has worked for decades. Except this time, the model was wrong. Here's what makes that matter. Most comet outgassing pushes an object in a fairly predictable direction, radially, meaning away from the sun. You can picture it as a rocket exhaust pointing backward along the comet's inward path. Scientists knew that 3I Atlas was experiencing non-gravitational acceleration, meaning forces beyond pure gravity. What they assumed was that those forces were mostly radial, push away from sun, standard comet behavior. The original model actually encoded that assumption directly, treating radial acceleration as roughly 5 times stronger than any sideways force. The new paper says that assumption was wrong by a factor of 5. The radial and tangential forces, the sunward push and the sideways push, turn out to be roughly equal, which means this object isn't just being pushed away from the sun, it's being pushed sideways, along its direction of travel. Imagine you're rolling a skateboard toward a target on the other side of a parking lot. Someone pushes it forward, fine, it gets there. Now imagine someone also pushes it hard from the side. It drifts, it no longer hits the target, it curves off course toward something else. 3I Atlas is curving off course, and the something else it's curving toward is Jupiter. The closest approach to Jupiter is projected for March 16th, 2026. That's roughly 10 days from now as this script goes out, and here is the number that changes everything. The object is projected to pass within approximately 257,000 kilometers of Jupiter's Hill sphere boundary, the invisible gravitational border where Jupiter's influence begins to dominate over the Sun's. That margin sounds large until you understand that the Hill sphere itself extends 53.5 million kilometers out from Jupiter. 257,000 kilometers is a razor-thin gap. We're talking about an object threading a gap that represents less than 0.5% of the entire boundary radius. And here's the central question that nobody has a comfortable answer to. The object is still outside Jupiter's gravitational influence. Jupiter isn't pulling on it yet. So if Jupiter isn't steering it toward Jupiter's own gravitational boundary, what is? Orbital mechanics is not a soft science. It is not a field where you shrug at errors and move on. When NASA's Jet Propulsion Laboratory produces trajectory calculations for a small body, those calculations are the product of some of the most precise applied mathematics on Earth. They incorporate gravitational influences from every significant body in the solar system. They account for the pressure of sunlight itself, a force so small it sounds like a joke, but over months it measurably shifts a spacecraft's position. JPL orbital predictions are so accurate that they've been used to navigate spacecraft to specific coordinates billions of kilometers away, threading them through gaps in planetary ring systems with margins of error measured in kilometers over journeys that took years. So when a peer-reviewed paper comes out and says the JPL model for 3I Atlas underestimated the sideways force by a factor of 5, that's not a routine correction. That's the kind of correction that prompts a careful, uncomfortable look at the assumptions baked into the original model. The specific concept at play is called non-gravitational acceleration, and it's worth spending a moment on what that actually means because it's the mechanism at the center of this entire story. When a comet gets close enough to the sun, the heat causes volatile materials, ices, frozen gases, to sublimate directly from solid to vapor. That vapor streams away from the comet's surface in jets, and those jets produce thrust. It's essentially the same physics as a rocket engine, just messier and less controlled. The comet is burning its own material as propellant, and the reaction pushes it in the opposite direction of the exhaust. In most comets, this outgassing is dominated by water ice sublimating under solar heating. The jets tend to point generally away from the sun, because that's where the heat is coming from. The thrust is mostly radial. Scientists have been modeling this successfully for a long time. The framework works. What it doesn't handle as cleanly is a situation where the jets are not pointing away from the sun. And that is exactly what appears to be happening with 3I Atlas. The new peer-reviewed solution found that the radial and tangential non-gravitational parameters, the technical terms for the sunward force and the sideways force, are approximately equal in magnitude. That means the outgassing isn't primarily pushing the object away from the sun, it's pushing it sideways. The original model encoded an assumption that the radial component was 5 times the tangential component. That assumption was inherited from typical comet behavior. It was applied to an object that is emphatically not behaving like a typical comet. Now here's the part that makes orbital mechanics specialists uncomfortable. The total force involved is approximately 1 micrometer per second squared. Write that out and it's 0.000001 meters per second squared. That is a genuinely tiny number. If you put a human hair flat on a table and measured its width, the acceleration we're talking about is smaller than that, applied every second. You would not feel it. You would not detect it without extremely precise instruments. It sounds like nothing. But orbital mechanics doesn't care what sounds like nothing. Forces that seem negligible on human timescales accumulate over weeks and months into positional errors of thousands of kilometers. A micrometer per second squared, sustained over the weeks since discovery, has pushed 3I Atlas far enough off its original predicted path that the Jupiter encounter outcome may be completely different from what scientists initially calculated. That tiny sideways nudge is the difference between the object threading safely past Jupiter's gravitational boundary and clipping the edge of it. That accumulation, tiny force, long time, massive consequence, is exactly why this trajectory correction matters so much. And it's why the question of what is generating that sideways force is not academic. It is urgent. Because if scientists can't correctly characterize the force that's been steering this object, they cannot reliably predict what it will do during and after the Jupiter encounter. The models failed not because of a data error. They failed because the physics of how this specific object is venting gas turns out to be unusual. The question is how unusual and why. To understand why the Jupiter encounter is so significant, you need to understand what the Hill sphere actually is. Most people think of planetary gravity as something that either affects you or doesn't. You're either orbiting Jupiter or you're not. But the reality is more like a series of nested zones of influence, and the Hill sphere is the boundary that marks where a planet's gravity begins to dominate over the sun's. Jupiter's Hill radius extends approximately 53.5 million kilometers from the planet's center. Within that boundary, if you're a small body moving slowly enough, Jupiter's gravity is the dominant force acting on you. Outside it, the sun wins. It's not a physical wall. There's no line you cross and suddenly feel Jupiter pulling at you. It's a mathematical threshold, the point at which the gravitational balance tips from one dominant force to another. 3I Atlas is projected to pass within approximately 257,000 kilometers of that threshold. Not within it, near it. That distinction matters enormously, and it's also where the uncertainty becomes critical. Because that margin of 257,000 kilometers, it was calculated using the old trajectory model, the one that underestimated the sideways acceleration by a factor of 5. With the corrected model, the one that properly accounts for the roughly equal radial and tangential forces, the revised trajectory brings the object thousands of kilometers closer to that boundary than previously thought. Thousands of kilometers sounds like a lot. In the context of a 257,000 kilometer margin, it begins to sound like a lot less, and the outgassing that's been steering this object doesn't stop just because scientists updated their math. It keeps pushing. There are essentially 3 outcomes for the March 16th encounter, and right now the uncertainty in the trajectory models means scientists cannot definitively rule any of them out. The first outcome is a clean miss. The object passes well outside the Hill sphere boundary. Jupiter's gravity barely registers as a perturbation, and the object continues on its modified path out of the inner solar system. The second outcome is a graze. The object's path clips the outer edge of the Hill sphere, close enough that Jupiter's gravity meaningfully tugs on it for a brief period, altering its velocity vector by a measurable amount. The third outcome, the most consequential, is a genuine entry into the Hill sphere, however brief. If that happens, Jupiter becomes the dominant gravitational force acting on 3I Atlas for a period of hours to potentially days, and every trajectory model for what happens next needs to be rebuilt from scratch. What's striking, and what makes scientists genuinely uncomfortable, is that the sideways acceleration, the force that the original model missed, is precisely the force that shifted the trajectory closer to the Hill sphere boundary rather than further from it. If the radial component had dominated the way the original model assumed, the object would be tracking further from Jupiter's gravitational boundary. The sideways component nudges it closer, and the direction of that nudge happens to point toward the one place in the solar system where a small course correction makes the biggest difference. Nobody is saying that's intentional. Nobody credible is claiming the object is navigating. But the geometry is uncomfortable, and scientists discovered the trajectory error only weeks before the encounter. That's not a lot of time to be confident in your revised predictions. The encounter happens on March 16th. Whatever is going to happen is already in motion. Here is something that gets to the core of why this situation is unusual, and it requires you to think carefully about the sequence of events rather than just the outcome. When a small body has a close encounter with a massive planet, that planet's gravity changes the small body's trajectory. That's normal. That's textbook. After the encounter, the body leaves on a different path than it arrived on. That's how gravity assists work. That's how Jupiter has been flinging comets onto new trajectories for billions of years. What is not normal is a trajectory change that begins before the gravitational encounter. 3I Atlas is still outside Jupiter's Hill sphere. Jupiter's gravity is not yet the dominant force acting on it. The Sun's gravity is. And yet the object's trajectory has already shifted. The course change detected in the new analysis predates the encounter. The sideways drift is happening now, while the object is still in a region of space where Jupiter barely registers as a gravitational influence. That means something other than Jupiter is changing the course before Jupiter gets involved. The official scientific explanation is non-gravitational outgassing, and it's almost certainly correct. The jets of gas and vapor erupting from the nucleus are generating thrust, and that thrust has a sideways component that's been accumulating over weeks. Scientists aren't confused about the mechanism in a broad sense. What they're still working to fully characterize is the specific geometry, the direction, the magnitude, and the reason this particular object's outgassing is producing such a pronounced transverse force. That last part matters because orbital predictions for small bodies, asteroids, comets, known periodic visitors are usually extremely reliable. When scientists say a comet will pass a certain distance from a planet on a certain date, the margin of error is typically small enough to be practically irrelevant. The machinery of orbital mechanics is precise. The models are tested against decades of observations. Errors of the magnitude found in 3I Atlas's trajectory, large enough to change the Jupiter encounter outcome, are not common. They are not expected. They suggest that something about this specific object's outgassing is genuinely unusual. What's strange is not just that the force exists. What's strange is the direction. The sideways acceleration is pointed in a way that, when accumulated over weeks, moves the object toward Jupiter's gravitational boundary rather than away from it. It's the directional coincidence that makes people pause. Think about it this way. If you were designing a trajectory for a comet to maximize its interaction with Jupiter, you would apply a small sideways force over an extended period to nudge it closer to the Hill sphere. That's exactly what the outgassing appears to be doing entirely on its own, apparently as a natural consequence of how the jets happen to be oriented on this specific nucleus. The scientific community is focused on characterizing those jets, understanding their geometry, figuring out why this comet produces such an unusual thrust profile. The answers to those questions exist in the object's physical structure, and some of the data collected in recent weeks has started to reveal what that structure actually looks like. The picture that's emerging raises new questions about what exactly is venting from this nucleus, and why it's pushing so hard in that particular direction. The three things discovered about the nucleus are about to make this story considerably more interesting. The Hubble Space Telescope has been watching 3I Atlas with as much attention as it can spare, and recently astronomers did something painstaking with that data. A comet in full activity is surrounded by a coma, a diffuse glowing cloud of gas and dust that puffs out from the nucleus and makes it look, from a distance, like a fuzzy ball of light. That coma masks the nucleus almost completely. You can't see the surface through it. So astronomers did what astronomers do when reality refuses to cooperate with their instruments. They subtracted the coma digitally. Layer by layer, they modeled what the diffuse glow should look like under standard assumptions, and they removed it from the images, leaving behind the structures that didn't fit the model. What they found in the residual images in the region immediately surrounding the nucleus were three distinct mini-jets, symmetrically arranged, individually resolved, streaming material away from what appears to be three separate active areas on the surface. This matters enormously for understanding the sideways acceleration, and here's why. 3I Atlas has a measured rotation period of 7.1 hours. The nucleus spins once every 7.1 hours. Now imagine those three jets as thrusters mounted on a spinning object. As the nucleus rotates, the direction each jet points rotates with it. A jet that's pointing sunward one moment is pointing sideways a few hours later, and pointing in the opposite direction a few hours after that. The thrust vectors constantly change direction as the nucleus turns. When you average the effect of a constantly rotating set of jets over many rotations, the net force depends critically on the geometry of those jets relative to the spin axis. Some configurations cancel out and produce no net thrust. Other configurations produce a net thrust that points sideways relative to the object's orbital motion. And it turns out that the configuration inferred for 3I Atlas, three jets at specific orientations on a nucleus spinning every 7.1 hours, produces exactly the kind of transverse force that the new orbital solution found. That's not a coincidence. It's the physics working out. The three jets, combined with the rotation, produce a vector sum that pushes sideways. This is the mechanism. This is why the object is drifting toward Jupiter's gravitational boundary. Not because of some exotic physics, not because of anything outside ordinary cometary behavior, but because three vents on a spinning nucleus are pushing gas out in three directions that happen to sum to a sideways thrust. The question that naturally follows is why those jets are oriented that way, and that answer lies in the geometry of the nucleus's rotation axis. Because the spin axis of 3I Atlas is not oriented the way most cometary spin axes are. And that orientation is the key to understanding everything that's been driving this story. The spin axis of 3I Atlas is pointed within approximately 20 degrees of the Sun. That sounds like a technical detail. It is actually one of the most important physical facts about this object because it determines how the jets behave across the entire orbit. Think about what that geometry means. The nucleus is spinning and its north pole is aimed roughly toward the Sun, which means the polar regions of the nucleus, the top and bottom of the spinning object, are the areas that receive the most direct solar heating. Those regions are warm, and warm regions sublimate volatiles. So the vents that are most active are likely located at or near the poles, the high-latitude regions that are constantly pointed toward the Sun's heat. Now think about what jets erupting from near the poles of a sun-pointing nucleus actually do. They erupt roughly perpendicular to the nucleus's equatorial plane. But because the spin axis points toward the Sun, that equatorial plane is roughly perpendicular to the Sun-comet line. Jets erupting perpendicular to that plane are erupting sideways, transverse to the sunward direction. This is the geometry that makes 3I Atlas unusual. The spin axis orientation essentially turns the polar jets into lateral thrusters. The analogy that helps here is a lawn sprinkler. Imagine a sprinkler with angled nozzles mounted at the top and bottom of the spinner rather than around the equator. When it rotates, those angled nozzles don't push water straight out, they push it in a sweeping sideways arc. Net force sideways. That's what these polar or high-latitude jets are doing on 3I Atlas. The Sun's heat activates the vents. The vents point sideways because of the axis orientation. The sideways gas produces sideways thrust, and sideways thrust accumulated over weeks drifts the object toward Jupiter. There's an additional complication that makes modeling this even harder. When a comet vents material unevenly, more from one high-latitude region than another, more from one side of the nucleus than the other, the uneven mass loss creates a torque. That torque changes the spin axis orientation over time. The nucleus wobbles. A wobbling spin axis means the thrust direction is not perfectly constant, it precesses slowly, changing the direction of the net force as the weeks go by. Scientists call this the Yarkovsky-O'Keefe-Radzievskaya-Paddock effect, or YORP, and it is notoriously difficult to model precisely for an object you've only been watching for a few months. Observations from earlier in the object's approach actually caught columnated outflows, tightly collimated jets that look more like searchlight beams than diffuse clouds. Those structures are consistent with high-latitude vents producing focused, directional eruptions. The same vents that create those visually dramatic columns are also the mechanism producing the transverse force that shifted the trajectory. Everything connects to the same physical source. And speaking of unusual structures observed on this object, there's something about 3I Atlas's dust tail that caught the attention of observers early on, something that seems to break the rules about which direction a comet's material is supposed to point. That anomaly isn't just visually strange. It connects directly back to the outgassing physics that's been steering this object toward Jupiter. Comets have tails. Usually those tails point away from the sun, swept back by solar wind and radiation pressure. But sometimes, under specific geometric conditions, when Earth passes through the plane of a comet's orbit, you can see an anti-tail, a structure that appears to point toward the sun rather than away from it. It's a perspective effect, caused by large dust particles that don't get swept away as efficiently as small ones, lagging behind in the comet's orbital path. Anti-tails are not unheard of. They're unusual, but they're explained by known physics and they've been observed on other comets. 3I Atlas has one. What made observers pay attention is that this anti-tail appeared unusually structured and persistent, not the kind of diffuse trailing sheet you'd expect from simple geometric projection of large dust grains, but something with more internal organization than standard models cleanly predict. Nobody is claiming the anti-tail is evidence of something exotic. The honest scientific position is that it's likely another expression of the same unusual gas and dust activity that defines this object's behavior. The same high activity, directionally unusual venting that's been producing the 3 mini-jets, the columnated outflows, and the transverse acceleration. The dust structures in the anti-tail are downstream products of the same outgassing processes that are altering the trajectory. If you want to understand why 3I Atlas is heading toward Jupiter's gravitational boundary, the anti-tail is another data point pointing at the same root cause. A nucleus that vents material in directions that standard comet models don't fully anticipate. And those same venting processes have been doing something chemically surprising that researchers didn't see coming. Spectroscopy is how astronomers eavesdrop on objects they can't visit. Every molecule emits and absorbs light at specific wavelengths, fingerprints in the spectrum that identify the chemistry of what's outgassing. Scientists have been running spectroscopic observations of 3I Atlas since it arrived, building a chemical portrait of what this interstellar visitor is actually made of. Before perihelion, that's the point of closest approach to the sun, the dominant signatures were carbon dioxide and carbon monoxide, CO2 and CO. Those are both volatile ices, both common in comets and, in the outer solar system, bodies thought to form beyond the frost lines of planetary systems. Carbon monoxide in particular is extremely volatile, meaning it's sublimated at relatively low temperatures, which is consistent with an object arriving cold from interstellar space and beginning to warm as it approaches the sun. The chemistry made sense. The picture was coherent. Then 3I Atlas passed perihelion, and the chemical portrait shifted in ways that didn't quite fit the model. Methane appeared. Hydrogen cyanide appeared. Methanol signatures strengthened. Methane in particular caught scientists off guard because methane is hypervolatile. It has a lower sublimation temperature than carbon dioxide. In the standard picture of comet chemistry, methane should have already sublimated before CO2 became dominant. If the object was warm enough to be releasing CO2 in large quantities, it should have burned through its methane reserves long before then. The fact that methane appeared after perihelion as the object was warming up rather than cooling down seems to invert the expected sequence. The explanation scientists find most convincing involves thermal wave penetration. Comets are not isothermal. Heat doesn't distribute evenly through them. When solar radiation warms the surface, that heat propagates inward gradually, like the way ground temperature in a field lags behind air temperature by weeks in spring. Deeper layers stay cold longer. If there are pockets of methane ice trapped beneath a CO2 or silicate crust, those pockets might not reach sublimation temperature until the thermal wave from perihelion propagates down to them. Post-perihelion methane could be methane that was in cold storage, finally thawing out as warmth penetrated through the crust. The complication is that this same logic should apply to carbon monoxide, which is more volatile than methane. CO should have been the last thing to sublimate, the deepest, coldest reservoir. But CO was detected first, before methane. That's the methane paradox that's been quietly circulating in the literature. The volatile sequence doesn't fully match any single simple model. Some Kuiper belt objects show similarly scrambled volatile inventories, suggesting that the internal structure of small icy bodies from the outer solar system, or from other star systems, can be more complex than the standard layered cake picture allows. Here's why any of this matters to the central story. The chemistry is not a separate puzzle. It's the same outgassing mechanism, the same venting, the same jets, the same active surface regions that are producing CO, methane, and hydrogen cyanide that is also generating the thrust pushing this object sideways. The force changing the trajectory is the same force releasing the chemistry. The methane appearing post-perihelion, the hydrogen cyanide signatures, the complex volatile inventory, all of that is physically happening at the same jets that have been nudging 3I Atlas toward Jupiter's gravitational boundary for weeks. The chemistry and the trajectory are not separate mysteries. They are the same mystery. Scientists who work on interstellar object trajectories are careful people. They are not, as a rule, prone to finding patterns where none exist. The entire discipline is built on rejecting assumptions and testing models against data. So, when several researchers independently noted that the orbital path of 3I Atlas passes unusually close to multiple planets in sequence, Venus, Mars, and now Jupiter, they were careful about how they said it. The orbital inclination of 3I Atlas is roughly 5 degrees relative to the ecliptic. The ecliptic is the plane of Earth's orbit, and approximately the plane that all the major planets orbit in. An interstellar object arriving from outside the solar system could theoretically arrive at any inclination, 30 degrees, 60 degrees, nearly perpendicular to the ecliptic. An object at 5 degrees is essentially threading the same orbital corridor that the planets themselves occupy. It passes close to the flat plane where planetary encounters are most likely. When researchers ran the statistics on how probable it is, by chance, for an interstellar object to arrive on a path that brings it within significant gravitational range of Venus, then Mars, then Jupiter in sequence, the number they got was approximately 0.005%. That's not impossible. It's not even particularly alarming in isolation. Unusual things happen in small sample sizes. We've only ever detected 3 interstellar visitors, which is not a large enough sample to say anything statistically definitive. When you roll a die 3 times and get 3 sixes, that's suspicious, but it's not proof the die is loaded. The astronomical community's consensus position is that this is coincidence. An interstellar object arriving near the ecliptic plane is unusual, but not inexplicable. Objects traveling between star systems can arrive from any direction, and those arriving near the ecliptic are simply more likely to be detected and more likely to have interesting planetary encounters. There's a selection effect at work. We find the ones that come close to planets partly because those are the ones we look for hardest. What the low probability alignment does do, practically speaking, is set up the geometry that makes the sideways acceleration so consequential. The reason 3I Atlas is approaching Jupiter's Hill sphere boundary rather than flying through the outer solar system, well clear of any planet, is precisely because its inclination puts it in Jupiter's neighborhood. An object at 40 degrees of inclination wouldn't be having this encounter at all. The alignment that some find statistically uncomfortable is the direct geometric reason that the sideways outgassing force is pushing this object toward Jupiter's gravitational boundary rather than off harmlessly into space. The trajectory math and the alignment statistics are not separate questions. They're connected by geometry. Harvard astrophysicist Avi Loeb is one of the most credentialed and simultaneously most controversial figures in planetary science right now. He was the chair of Harvard's astronomy department. He has written and published serious peer-reviewed work on some of the most challenging theoretical questions in astrophysics. He is also the person who publicly argued that Oumuamua might be a piece of alien technology, a light sail specifically, and who has continued methodically to push the argument that the anomalous behavior of interstellar objects deserves to be taken seriously as potentially artificial in origin. He's been paying close attention to 3I Atlas. Loeb's argument about the trajectory is essentially this. Without the sideways acceleration, if the object were behaving the way the original NASA model assumed, with radial force dominating, it would pass Jupiter's Hill sphere at a comfortable distance. The Hill sphere encounter would be a near miss, with the sideways acceleration, the equal tangential force revealed by the new peer-reviewed analysis, the trajectory shifts enough that the object approaches the Hill-sphere boundary closely. The sideways force, in other words, is precisely what makes the Jupiter encounter interesting rather than unremarkable. Remove that force, and nothing happens. Apply that force and the object steers toward the one gravitational boundary in the solar system that could fundamentally alter its trajectory. Loeb himself acknowledges that the object is most likely natural. He says that clearly. His argument is not that 3I Atlas is a spacecraft. His argument is that the coincidence deserves serious analytical attention rather than dismissal, and that the history of Oumuamua shows what happens when anomalies get written off too quickly. The acceleration appears, in his framing, finely tuned in the sense that it produces exactly the effect needed to shift the trajectory meaningfully without being so large that it would require an obviously exotic explanation. The mainstream scientific response to this framing is that post hoc pattern recognition in small samples is unreliable. Given any trajectory, you can construct an argument that the forces acting on it appear fine-tuned for some purpose. That reasoning doesn't distinguish genuine design from coincidence. The jets on 3I Atlas are consistent with known cometary physics. The sideways force is explained by the spin axis geometry and the three-jet configuration. Extraordinary claims require extraordinary evidence, and what we have is an unusual comet with explicable, if unusual, outgassing behavior. But Loeb's argument exists entirely because the sideways acceleration is steering this object toward Jupiter. That's the fact that gives his framing whatever traction it has. And it's the same fact that's driving this entire conversation. The trajectory correction is real. The steering is real. The question is only whether the explanation is a natural but unusual comet, or something else. The encounter on March 16th is the natural experiment that begins to answer that question. Loeb has floated a more speculative idea that sits at the fringe of serious scientific discourse, and it's worth understanding what it actually claims before deciding whether it deserves your attention. The idea is called the Sentinel hypothesis, and it suggests that a sufficiently advanced civilization might scatter autonomous probe objects throughout the galaxy, designed to approach planetary systems, conduct reconnaissance, and either report back or take some action. In this scenario, Jupiter's Hill sphere is not just a gravitational curiosity. Jupiter is the largest planet in the solar system, the most gravitationally dominant body aside from the Sun, and its Hill sphere would be a natural staging location for an object that wanted to observe the inner solar system from a stable gravitational vantage point. The parallels to science fiction, specifically Arthur C. Clarke's monolith in 2001, are obvious, and Loeb has not shied away from acknowledging them. There is no observational evidence supporting this hypothesis. None. The jets, the outgassing, the spin axis geometry, all of it is consistent with a natural comet, and none of it requires an artificial explanation. The hypothesis is mentioned here because it's part of the public scientific conversation, and because refusing to acknowledge it doesn't make it go away. But the reason it exists in that conversation at all is the sideways acceleration, the fact that something has been steering 3I Atlas toward Jupiter's gravitational boundary from outside Jupiter's gravitational influence. Take away that trajectory anomaly, and the Sentinel hypothesis has no foothold whatsoever. There's one more thread attached to the chemistry findings that's worth naming briefly. The molecules detected in 3I Atlas's outgassing, methane, methanol, hydrogen cyanide are not just scientifically interesting as volatile tracers of the object's thermal history. They are also among the building blocks of prebiotic chemistry. Hydrogen cyanide in particular plays a role in laboratory synthesis of amino acids and nucleobases. Methanol is present in molecular clouds where stars and planets are forming. The theory of interstellar panspermia holds that organic chemistry, or in more extreme versions, actual microbial life, could travel between star systems on the surfaces of comets and asteroids, seeding chemistry across the galaxy. 3I Atlas, arriving with a cargo of exactly these kinds of molecules, is precisely the kind of object that panspermia theorists point to. It's brought chemistry from another star system into our solar system, releasing those molecules as it heats up near the Sun. The panspermia hypothesis remains unproven and contested. The connection to the central story here is direct, though. The organic molecules being detected are products of the same outgassing that has been altering 3I Atlas's trajectory. The jets releasing methane and hydrogen cyanide are the same jets producing the thrust that's pushing this object toward Jupiter. The chemistry and the trajectory are outputs of the same physical process. What this visitor from another star is made of and where it's going are, in a very literal physical sense, the same question. Let's talk about what actually happens if 3I Atlas enters Jupiter's Hill sphere, even briefly. The Hill sphere isn't a trigger. Crossing the boundary doesn't cause an explosion. There's no alarm that goes off. What it means is that Jupiter's gravitational pull becomes the dominant force acting on the object, stronger, at that point, than the sun's pull on it. For an object moving at 3I Atlas's velocity, which is approximately 70 kilometers per second relative to the sun, that dominance period would be measured in hours to days rather than months. The encounter is fast, but fast doesn't mean inconsequential. During the encounter period, Jupiter's gravity acts on the object continuously, changing its velocity vector, the direction and speed of travel. This is a gravitational deflection. The magnitude of that deflection depends on how close the object passes to Jupiter itself, how long it spends under Jupiter's dominant influence, and the precise angle of approach. Models of this encounter suggest that even a brief entry into the Hill sphere could alter the object's exit trajectory by a measurable and potentially significant amount. There are several possible outcomes in descending order of drama. In the mildest case, the object grazes the outer Hill sphere, receives a modest gravitational nudge, and exits on a slightly modified trajectory with a refined velocity vector meaningful to scientists building models, but not dramatically different from a clean miss. In a more significant case, the object passes deeper into the Hill sphere, closer to Jupiter, and receives a gravitational kick large enough to substantially alter its path through the outer solar system. In the most dramatic but least likely case, tidal forces during a close approach could stress the nucleus, potentially triggering increased outgassing activity or even partial fragmentation, producing a debris field that spreads along the trajectory. Scientists simulate these encounter scenarios using orbital integration models, running thousands of possible trajectories through the uncertainty range to build a probability distribution of outcomes. What the new peer-reviewed trajectory analysis has done is shift that probability distribution toward closer encounters than the original model predicted. The revised trajectory means more of those thousands of simulated paths clip the Hill sphere than before. And every model run has to account for the fact that the outgassing doesn't stop during the encounter. 3I Atlas will still be venting gas and producing thrust while Jupiter's gravity is simultaneously acting on it. It's a three-body problem with a non-gravitational force, which is among the hardest categories of problems in orbital mechanics to solve precisely. The encounter begins on March 16th. Within days of that date, the observational data will either confirm or refute the revised models, and either way, scientists will learn something important about how to handle the next interstellar visitor. 70 kilometers per second. That's 3I Atlas's velocity relative to the sun. To put that in terms that connect to anything human scale, a commercial aircraft flies at roughly 0.25 kilometers per second. 3I Atlas is moving at approximately 280 times that speed. It is crossing a distance equivalent to Earth's circumference every 9 minutes. At that velocity, gravitational capture, the scenario where Jupiter's gravity slows the object enough to trap it in orbit, is essentially impossible for the whole object. Escape velocity from Jupiter's Hill sphere for a body at that distance is far lower than 3I Atlas's velocity. The object will pass through any gravitational interaction like a bullet through fog, deflected but not stopped. Scientists aren't worried about Jupiter catching 3I Atlas. They're focused on the deflection. The difficulty of modeling the encounter comes from several compounding factors. First, the object's outgassing is still not fully characterized. The new peer-reviewed model improved the trajectory prediction significantly, but it's based on observations up to a certain date, and 3I Atlas has shown a pattern of chemical and structural changes over time. The methane that appeared post-perihelion changed the outgassing profile. Future changes in activity could shift the trajectory further. Second, multi-body gravitational interactions involving non-gravitational forces exhibit sensitive dependence on initial conditions. The technical term is chaotic dynamics. Small differences in the initial state of the system, the precise velocity, the precise direction of the thrust, the precise mass distribution of the nucleus produce large differences in outcome over extended time periods. This is not a failure of the models. It's a fundamental feature of the physics. The universe is not always predictable at the precision scientists require. Third, the encounter duration is short. A gravitational encounter that lasts hours gives observers very few data points to constrain the models in real time. The object enters the encounter zone, something happens, the object exits. The observational window for catching the encounter's effects midstream is narrow. Most of what scientists will learn will come from comparing the post-encounter trajectory with the pre-encounter predictions. That comparison, predicted trajectory versus observed trajectory after March 16th, is going to be one of the most scientifically valuable datasets ever collected on an interstellar object. Because the lesson of this entire episode is that the models can be wrong, and the consequences of that can be large. The encounter is the test. One of the questions that surfaces in discussions of the Jupiter encounter is whether Jupiter could capture 3I Atlas, not just deflect it, but actually trap it as a gravitational prisoner of the solar system. Answering that question requires confronting some very large numbers. The kinetic energy of 3I Atlas, traveling at approximately 70 kilometers per second, is enormous. Researchers have calculated the approximate energy required to reduce the object's velocity enough to achieve gravitational capture, to slow it from interstellar velocity to solar system orbital velocity. That figure is approximately 1.66 times 10 to the 22nd joules. Written out, that's 16 million trillion million joules. For comparison, total global human energy consumption in a year is approximately 6 times 10 to the 20th joules. Capturing 3I Atlas would require roughly 270 times humanity's annual energy output applied instantaneously. Jupiter doesn't have that energy budget to give to a gravitational interaction. No planet does. The object will not be captured. It will pass through, be deflected, and continue out of the solar system on a modified trajectory. This is worth stating clearly because speculation about capture sometimes circulates in these conversations, and the physics rules it out firmly. What the energy calculation does not rule out is the behavior of small fragments, if any fragmentation occurs. A boulder-sized piece of 3I Atlas that gets dislodged during tidal stressing has a much lower kinetic energy. Under the right circumstances, small debris could potentially be slowed enough to enter elongated solar system orbits. This is speculative, requires specific conditions, and scientists are not predicting it. But it's not physically impossible in the way that whole object capture is, and it's a scenario that trajectory modelers have run through for completeness. The more practically relevant outcome of the encounter is the gravitational assist effect, not capture, but trajectory modification. Jupiter regularly deflects comets during close encounters, sometimes sending them onto shorter period orbits closer to the Sun, sometimes ejecting them from the solar system on hyperbolic trajectories. A meaningful deflection of 3I Atlas would change where we observe it going after the encounter, potentially giving scientists a longer observing window as it loops back through the inner solar system, or ending the observing opportunity earlier if it gets flung outward on a faster exit vector. The direction of that deflection depends on which side of Jupiter the object passes, and that depends on whether it enters the Hill sphere, and by how much. All of which leads back to the uncomfortable fact: we don't know yet. The prediction was revised once. It could be revised again after the encounter. Let's step back from the spectacle and frame what the scientific community is actually grappling with, because the real story here is not about alien probes or gravitational capture, or any of the more dramatic framings that this scenario invites. The real story is about prediction. Orbital mechanics is one of the oldest and most mature branches of physics. Kepler mapped planetary orbits in the 1600s. Newton gave us the mathematics to predict them precisely. For 300 years, scientists have been refining those models, adding corrections for non-gravitational forces. running increasingly precise calculations on increasingly powerful computers. The field is not unsophisticated. When JPL says a small body will be at a specific location on a specific date, the track record for being right is extraordinary. 3i Atlas broke that track record in a way that matters. The new peer-reviewed analysis didn't find a minor refinement. It found a factor of 5 error in the characterization of the thrust forces acting on the object. And that factor of 5 error was large enough to change whether the object clips Jupiter's gravitational boundary on March 16th or misses it cleanly. That's not a rounding error. That's a model failure. The anomalies stack up when you put them all together. The sideways acceleration that wasn't anticipated, the unusual spin axis geometry producing transverse thrust, the 3 symmetrical jets generating a vector sum that points toward Jupiter, the volatile chemistry that inverts the expected sublimation sequence, the orbital inclination that places the object in the planetary corridor. Each of these individually has a plausible scientific explanation rooted in known physics. None of them individually require anything exotic. But collectively, they describe an object whose behavior has consistently pushed against the assumptions of the models applied to it, and those models had to be revised. The Jupiter encounter on March 16th is now a natural experiment designed, not by scientists, but by physics. After the encounter, astronomers will have an observed post-encounter trajectory. They will compare that trajectory to what the revised models predict. If the models are right, the encounter will confirm the new understanding of the outgassing forces and provide the best constrained dataset ever collected on an interstellar object in a planetary encounter. If the models are wrong again, the scientific community will have learned that its understanding of how interstellar objects behave near giant planets needs to be rebuilt from scratch. That's the real science happening here. Not whether the object is artificial, not whether Jupiter captures it. The real question is whether the models are finally right or whether 3i Atlas has another surprise waiting on the other side of March 16th. Here's what we know for certain. A visitor from another star has been moving through our solar system. It has been venting gas and dust in unusual directions, driven by a spin axis geometry that produces sideways thrust instead of radial thrust. That sideways thrust has been slowly, persistently for weeks, nudging its trajectory toward the most gravitationally dominant planet in our solar system. Scientists thought they understood the trajectory. They were wrong. They corrected the model. And now, within days, the encounter will tell us whether the correction was enough. The object is about to reach the one place in the solar system that could change everything about its trajectory, and we still don't fully understand why it's heading there. What we do know is that whether the answer is unusual chemistry, unusual jets, an unusual spin axis, or something we haven't thought of yet, the universe has reminded us, once again, that the confidence of a prediction is not the same thing as the correctness of one. And the most dangerous assumption in science is the assumption that you already understand what you're looking at.